Hello everyone and welcome back. Now in the previous video I introduced you to new applications of the SINDy method to mapping discovery. And what I would like to do in this video is take that even further and combine it with our sliding window dynamic mode decomposition we learned a few lectures ago. And the result of today's lecture will be what's called data-driven averaging. Now, I've done a lecture on averaging before, and so I'm going to link to it in the description if you want to find more out about the theory of averaging. I'm going to provide a brief overview here of what averaging is for dynamical systems and what kind of systems it can be applied to, but we are mostly going to focus on the data science piece of this. So, just as a brief reminder, or maybe for your first time, averaging as a dynamical systems technique is typically applied to dynamical systems that look like this. Here, epsilon is a very small number. Okay, so we say it's much less than 1. Again, much like the previous video with the stroboscopic mappings, here we have periodicity in the t component, so the non-autonomous component. I'm just going to say that its period is going to be t greater than or equal to 0, or greater than 0, sorry. So again, this is a pumping and driving, a forcing term that's being applied to your dynamical system. But the epsilon here means that this is what's called a singularly perturbed dynamical system, okay? So it means that if I set epsilon equal to 0 and just try to work with this, I would just get x dot is equal to 0. I would have nothing to analyze, right? Doesn't tell me anything about the dynamics of this system. So singularly perturbed dynamical systems are a huge area of research in mathematics still to this day. A lot of the work on averaging was done in the 70s and the 80s, but now a lot of people are focusing on things that are called canards and all of these very complicated geometric singular perturbation theory, all these very complicated applications of dynamical systems. But the good news for us is that averaging has been primarily worked out, because what we know is one way to analyze this system is to work with the averaged system instead. And what I mean by this is define a new dynamical system. I'm going to call it Y. And this dynamical system looks like this. Epsilon over capital T, the integral from capital T of f of y, t, 0 dt. Okay, so here's the thing. I got rid of all higher order terms in epsilon here, right? I kept the leading order one. And I literally integrated over a whole, I actually averaged, right, because I divided by t, over a whole period of the forcing. It's very similar, but a little bit more subtle to what we saw with a stroboscopic mapping, okay? This is now an autonomous dynamical system. Don't be fooled, there's no t dependence anymore because you're integrating, it's a definite integral here. And it turns out that you can compare the solutions between x and y. In particular, what you can find is that x of t is basically y of t plus some small little order epsilon corrections. And in fact, we know those order epsilon corrections are periodic little wiggles, okay? So really what you can think about is that the original signal, the solution to this dynamical system, is the averaged part plus a part that has little micro oscillations coming into it. And those micro oscillations come from the periodicity. The reason we don't see them here is because we average them out. You can imagine this as an ironing process. So let me give you a really simple example just so we can get ourselves running. I'm going to give you a concrete dynamical system. It's going to be one-dimensional. It's going to be a periodic version, sorry, we want an x in here first, a periodic version of the logistic mapping. So I'm going to use, again, I'm just like in the last video, I'm going to set things so that my period is always just 1 to make my life very easy. And if I didn't have the sign here, this would be the logistic mapping that one sees in math biology all the time. And so what this periodicity here on this means is that this could be some sort of seasonal fluctuation that's taking place, right? So when t is near 0, this thing is basically negligible. And so you have your usual logistic equation and your population wants to grow. But when this sine term gets close to -1, it kills off this value, and actually your population wants to shrink. And then when sine gets large, your population wants to grow again. So you can imagine this is like, an annual pattern of in the summer, your species thrives, and in the winter, the weak ones die out. That's sort of what this is describing here. The epsilon is related to the growth rate over the time scale here. So here we're saying that it's a very sort of small growth rate. Now the averaged dynamical system, well, I can allow you to have your fun with this. All you need to do is integrate the right-hand side with respect to t from 0 to 1. And essentially, you get regular old logistic dynamics. And in particular, regular old logistic dynamics are fully solvable. So that's nice, right? So here, what you could do is this would be your initial condition. So I'll say y naught divided by y naught plus 1 minus y naught e to the minus epsilon times t. I don't need a bracket there. Now, let's analyze what all of this information tells us, okay? First of all, the solution y of t, well, we can see that the limit as t goes to infinity of y of t is equal to 1 for all initial conditions that are greater than 0. Okay? So if y naught is equal to 0, then you're at your fixed point and your population is extinct, right? Populations don't come out of anywhere or nowhere. So this says that your population always stabilizes to the carrying capacity. In this case, it's just normalized to be 1. So the maximal amount of species that, 100% of your species that your region can support. So what does that mean for my periodic system, my seasonal fluctuation system? Well, averaging tells me this. Averaging tells me that the solution to the periodic system is basically the average signal plus little wiggles, right? So what does the solution x look like to this thing? It is going to be, so if I can just sketch this out for you, if this is t and this is maybe x of t, if I start with a low population down here, and here is 1 right here, effectively what's going to happen is I'm going to grow monotonically up to 1 in the y component, and I'm just going to oscillate back and forth in the second piece. So I get little oscillations that go up and wiggle around 1. And the reason we're wiggling around 1 is because we can't sit right at the carrying capacity, because in the winter we kill some off, and then in the summer we grow back up so that we can afford to have some killed off. Okay? So a very, very simple model, but a nice model to really understand how averaging works in a dynamical system. Now, as I said, averaging was worked out in the 70s and the 80s. Most of this is already known. It's all done. We have all kinds of extensions of it. You can do this for all kinds of very, very complicated systems. But here's the question. Imagine I give you a signal that looks like it should be able to be averaged. And what I mean by that, I'm going to give you a signal, I'm going to call it phi, that looks like this. And what I mean by looks like this is it's periodic in what we'll call the fast component, but it has a slow background drift. This is exactly what we saw with the solution right here. The epsilon t right here represents a slow background drift. That is the slow rise to the carrying capacity. But in the short term, you have these fast oscillations. This is the same thing that you would see with the tides, right? Tides go in and out twice a day, but in the background, you have this slow drifting due to other gravitational forces. This is something that we talked about with sliding window DMD as well, right? Now, here what we're assuming is we're given a signal that is sort of periodic on the fast timescales, but has some sort of slow drifting going on in the background, right? And what averaging, again, if you think about what averaging does, it tells you what the slow drift is doing, right? It says, I don't care about the wiggles. I care about the long-term properties of these things. So here's what I want to do. If I just give you the signal, if I just give you the data, how can I average it to discover the slow drift? Well, here's what I'm going to do. I'm going to collect data from the signal, and my data, I'm going to call it x sub n, is going to be the signal after every single period, nt, and then epsilon nt. Right? So basically what I'm doing is I'm collecting data from the signal after every period of oscillation, right? So 1 period, 1 period, 1 period, 1 period, 1 period, and so on and so forth, right? And then what I'm going to do is I'm going to discover a mapping that iterates us through this coarse-grained signal, right? This is basically a stroboscopic mapping. This is exactly what we did in the previous video. But here's the thing. If we know, or let's imagine in theory, that the slow time dynamics, the average dynamics, right? So the average dynamics represent the slow time dynamics because they have the epsilon t in them. Let's imagine that they are governed by some dynamical system. So here I'm going to use this partial derivative notation. I'm going to say partial 2, representing the derivative with respect to the second component here of phi is equal to some function of phi. Okay, so imagine this is basically your average dynamical system for your signal. Okay, that's what I'm saying here. I'm calling it the slow time dynamics because it evolves on the slow time scale. So imagine we knew that. Then what could we say about our signal? Well, we can play a little game. We could say that xn plus 1 is just phi of n plus 1 times t, comma, epsilon n plus 1 times capital T. But because we're periodic here, this is the same as putting a 0 in here, right? Because this repeats the first component, epsilon n plus 1 of t. Then, oh, we don't need this. Then what we can do, because epsilon is very, very small, we could, for example, do a Taylor expansion around epsilon nt. Okay, so take a look at this. I'm going to write Taylor. Okay, so if I do a Taylor expansion here, the first one is evaluation. So 0 epsilon nt, right? So this is n plus 1. I'm going to go epsilon nt. That means that here is the first evaluation, and then plus epsilon t, partial derivative with respect to the second component of phi of 0 epsilon nt plus dot, dot, dot. And the dot, dot, dot is order epsilon squared terms. Maybe I should write it just so that you can see what's happening here. And now, let's take a look at this. This becomes xn, right, by definition. This is xn, because this is also equal to 0 inside of the signal. And then plus epsilon t, and then this is g of xn. Okay, did we get anywhere with this? Yes, because this guy right here is f of xn. So I get f of xn is this thing, sorry, plus an order epsilon squared. Now, think about the things that we know. I know capital T. I hope that I know epsilon. I know xn, and I know f. That means that I can rearrange this thing if I drop the order epsilon squared corrections here, and I could get g, the slow drift dynamics in the background, as f minus x divided by epsilon capital T, up to an order epsilon squared correction. That means that if you give me a signal and I know the period here, I can tell you what the slow background drift is going to be just by following this procedure. I know it looks like a lot of math, but mostly what I did here is just a derivation. In particular, I coarse grained the signal and I applied SINDy. Okay, we can do that. We did that in the last video. Then all I did, you can skip all of this derivation. Once I have the thing identified, then I can find the slow background drift. I can find the average system. I have a way of doing averaging with only the data. I didn't need the dynamical system anymore. I just needed SINDy to help me out. So let's actually see how this works on a demonstration. All right, let's take a look at a MATLAB demonstration here. And we're going to do this on the logistic model that we saw previously. Okay, so let's take a very small value of epsilon here. I'm going to integrate up the system in the same way we did for the stroboscopic mapping to generate my signal. I'm going to do this for a whole bunch of random initial conditions. And let's take a look at what the signal actually looks like. So here is the signal evolving to carrying capacity very slowly, right? So you can see time goes up to 2,500 here. And it's very hard to see, but that's because I took epsilon super small. There's these little micro oscillations taking place in here as well, right? So again, remember, averaging tells us that the signal is decomposed into a slow drift and a fast oscillation that's very, 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 very small. Okay, so now let's apply the SINDy method for discovery here. So again, I coarse grain the signal. I sample the signal after each period of the forcing here. In my case, it's just at each integer value. And now what I'm going to do, sorry, I think I mixed something up. We forgot to run this piece. Let's run SINDy now. And let's take a look. Here's our results, okay? So first of all, here's our SINDy mapping. Now it doesn't mean a whole lot to us if we just look at it like that. But if we rearrange to get the slow timescale dynamics, take a look at what we have here, okay? So we've got, if you want to factor this, it's about 0.998x 1 minus x-ish, right? So here you can see the logistic term. Here you can see the 1 in front of this thing. Remember, we divided off the epsilon already, so we don't have to worry about that epsilon out front. But essentially, this is doing a very, very good job because it has discovered the logistic map. Another aspect of this that I did not emphasize originally is that this method of data-driven averaging actually picks the value that you should use for your sparsity parameter. Because if you remember that big Taylor expansion that I did over here on the board earlier, what I did is I truncated at second order in epsilon. That truncation is a way of stamping out terms. And that stamping out terms is the sparsity that's imposed by the SINDy method. So here what you can see is I'm taking the sparsity parameter to be the square of the timescale separation parameter, epsilon, okay? So no thinking required, no choice of sparsity parameter. I can just use the square of this timescale separation. Now here what I want to do is I want to increase the value now of epsilon, and let's see what happens now. So again, here we're going to print off. Here you can see that in this case, we converge to the carrying capacity a little bit faster. And also you can see the oscillations, the little wiggles, you can see them a little better, right? There they are. They're a little bit bigger. That's because epsilon is a little bit bigger. But you can see that these things are still on the order of epsilon, so about 0.1, right? You can see going above the carrying capacities, we're about 1.01, a little bit more. Going below, we're about 0.985 or so. Then, if we throw this into the SINDy method, again, let's take a look at what SINDy returns for us. Here it is. Now, let's take a look at this model. Here is our discovered slow time mapping. This is something about maybe 0.8, let's say 0.83 times x, 1 minus x. So this guy right here is not the 1 that it should have been. Why? Well, that's because there are higher order corrections in epsilon, right? This is off by about a factor of epsilon. Okay, epsilon was about 0.1. This is off by the order of epsilon. And that should make sense, right? Averaging is only an approximation of a signal, and averaging only works, much like the Taylor expansion, when epsilon is very small. How small is small? Well, of course, that's context dependent. But here we can see that by increasing epsilon, we've decreased the accuracy of this mapping, which is to be expected. So let's just try one more value of epsilon right in between the two that we just did. So here I've got epsilon is 0.01. Let's retry this. Let's take a look at that signal. Here it is. Again, epsilon is smaller, so the periodicity is less pronounced. Here you can see those little micro oscillations again, and here you can see them on the order of epsilon as well. So if we run this again, let's take a look at what the slow timescale model turns out to be. Here again, if I just write this out for you, the leading value is about 0.98. That means that it's off by this second digit. Remember, epsilon was 0.01, so we're off by a factor of epsilon, a multiple of epsilon again. So you probably didn't notice this in the first application, but we had like 0.998 or something like that. We got about 2 digits of accuracy. We had an issue at the third digit, and that's because epsilon was 10 to the minus 3. So we should expect an accuracy for these data-driven averaged models on the order of epsilon in your coefficients. The smaller epsilon is, the better the model is going to be. Epsilon here is a scale disparity, right? It represents how different the movement is, how quick the oscillations are relative to how slow the convergence is. Now let me just show you one more example because I want you to think about something very interesting here. In order to apply all of this, I have to know what the fast period actually is, what capital T is. Because if I don't know capital T, I can't coarse grain the model. And if I can't coarse grain the signal, then I can't apply the method. So the question is, what if I don't know the fast period? Well, I have great news. We already figured out a way to do it. We can use sliding window DMD. Sliding window DMD picks out the period of oscillations in signals that have scale disparities. It's very, very good at finding that fast scale oscillation. Go back to that video on sliding window DMD and see for yourself. So here's what I want to do. I want to take an example of something that myself and Nathan Kutz and Daniel Diluski, one of the original authors on the sliding window DMD paper, what we were able to do. What we did is we took high fidelity data of a 3-body problem of a very accurate simulation, long-time simulation of a 3-body system that is the Sun, Jupiter, and Saturn. Okay, the 3 most massive bodies in the solar system. Now you know that Jupiter and Saturn will just orbit the Sun on a short time scale. Okay, that's the fast period oscillation. But of course, when Jupiter and Saturn get close to each other, they have a small gravitational influence that is weaker than the Sun, but what it does is it causes what's called an eccentricity in their orbit. And so what that means is that if you plot the orbits of Jupiter or Saturn, so if I can find it here, I'll pull it up for you just a second, you can see a little wiggle in it on very long timescales. Let's see where it is. Plot. So I'm plotting Jupiter data. I'm plotting this in the orbital plane, so in the XY plane. Pardon me. So here, okay, this is very, very weird looking data. It looks like a flag waving, but you can see that this is on a time scale of 10 to the 5. Let's take a look at what's happening here. If I take just a teeny, tiny, tiny, tiny little slice here, now you can see the oscillations that are taking place. These oscillations are the movement of Jupiter around the sun. This is the fast period oscillations. What you're seeing in the background with this slow drifting phenomenon is the gravitational interaction, the weak interaction from Jupiter and Saturn, the slow drift. So fast scale, predictable, periodic, going in a circle or going in an ellipse around the sun. Slow scale, the weak interactions, much more complicated. And in fact, you can get the same thing out of the data for Saturn as well. And what we know, we can throw sliding window DMD at this thing. We can extract the fast periods of oscillation. In fact, we can actually show, or what Daniel showed with his work, the fast periods that come out of that are very, very accurate, and they are very close to the known periods that we are seeing, of Jupiter and Saturn in the sky. So here, I believe I even have it. Yeah, so the period for Jupiter is about 11.85 human years, or Earth years, sorry, to make one trip around the sun. And so let's coarse grain that signal. Let's throw SINDy at it. And let's determine the slow timescale evolution. Here it's a two-dimensional differential equation because, again, it's in the orbital plane, so all of the movement is happening in a plane here. We have XY coordinates in the plane. Here you can see this is the ODE, the right-hand side of the ODE, that comes up using this method. Again, I don't know what the answer is, but this is what comes out of it. Our work shows that this is very accurate and predicts for a long time what's happening. In fact, what this is a conservation law, and it shows that you have a periodicity on a longer time scale as well. So you have this fast scale periodicity for going around the sun, and then you have this sort of slow scale wobble coming from this gravitational interaction of Saturn and Jupiter getting close to each other. You can do the same thing with Saturn's data. So if I take a look at this, if I just go up for a second, here, let's take a look. Let's load Saturn's data. Here, the orbital period of Saturn is about 29.5 Earth years. So if I just repeat all of this and then take a look at this, again, I basically get a very, very similar slow drifting here. Again, it's a linear model. It predicts that you have periodicity on this next time scale as well. And again, I want to emphasize Daniel's work and the work of numerous astronomers before them have also confirmed this, that on this secondary time scale, you also see a periodicity, but on a very long period. I think the period here is like 48,000 years compared to the just 29.5 years it takes for Saturn to go around the sun. So essentially what we've seen in this video is a way of doing averaging without the equations. It's a data-driven averaging method that leverages a method that we already learned, sliding window DMD. We see that this can be a very powerful method as long as there is a large-scale disparity between the fast-scale oscillatory motion and the slow-scale drift. Now, we saw with this last example that this is a natural candidate for things like celestial dynamics, gravitational interactions, because these things happen on such large, extremely different timescales. Now, when we come back in the next video, we're going to start talking about discovering conserved quantities. And we will see how this relates to the Koopman operator, but also to the SINDy method and EDMD. So I'll see you all in the next video, everyone.